Hello everyone. Today is the last lecture of our carbohydrate series, and it's entitled Carbohydrate Availability and Training Adaptation, which to me I think is one of the most groundbreaking topics of the last 5 years. So as a background, one of the things that has been purported in the literature over and over again is the benefits of high carbohydrate availability. Now, what those benefits are include greater training intensities, faster recovery times, and ultimately the promotion of adaptations. And the thought on promoting adaptations is that if you're training harder with a greater stimulus, you'll have greater long-term adaptations. While this sounds very nice on paper, the problem is that we have limited long-term research that supports this. Let's talk about the training adaptive process. What is it? From a cellular perspective, training adaptations can be viewed as a consequence of the accumulation of specific proteins required for sustaining energy metabolism during and after exercise, particularly proteins associated with the mitochondria as well as those associated with fat metabolism in general. Now, what you have to understand is that glycogen availability plays a critical role in regulating fat metabolism and oxidative phosphorylation. In fact, glycogen interacts with several proteins that regulate fat metabolism and oxidative phosphorylation, such as ATP synthase, NADH cytochrome B5 reductase, 3, and overall metabolism, such as AMPK. So the point is glycogen is interacting with all these proteins that regulate fat metabolism, oxidative phosphorylation, and metabolism in general. This is a real good figure by Philip et al. And what you're looking here is that is a hypothesis that glycogen availability may modulate the training response. It's thought that transcription factors in a low glycogen state are liberated and switch on genes that regulate fatty acid metabolism. If you look at part A of this figure, part A represents high glycogen levels, and as you notice, AMPK has a binding domain on glycogen. Thus, AMPK cannot interact with the nucleus. In addition, there's low fatty acids inside of the cell and outside of the cell. However, in B, we see low glycogen, which liberates AMPK to bind and switch on genes that regulate fat metabolism. In addition, fatty acids are going to be liberated. Those actually can turn on and regulate genes as well, which regulate fat metabolism. So how can we manipulate carbohydrate availability? If I'm constantly giving myself tons of carbohydrates, I constantly have a high amount of glycogen. So the thought is that if you deplete glycogen, you upregulate these transcript factors. Well, clearly that can be manipulated through diet. So how can I manipulate that? Well, one, I could have chronically low carbohydrate diet, like a ketogenic diet, for example, which we'll discuss later. In this case, your carbs are less than the fuel requirements that you need for training. The second way is twice-a-day training. And what you do here is you have low endogenous carbohydrate availability for the second session in a day by limiting the duration and carbohydrate intake and the recovery period after the first session. So in other words, I train session 1 in a normal glycogen state, I deplete glycogen, I don't consume any carbohydrates, and then I come back and complete a second session. So that means low endogenous carbohydrate. I could train after an overnight fast, which lowers exogenous carbohydrate, meaning what's in your blood. Or we could have prolonged training with or without an overnight fast. You know, if you're running 20-something miles, you're going to deplete glycogen. And I can also withhold glycogen during the first few hours of exercise. we're going to talk about all these manipulations. Classic study. First study was performed by Hansen in 2005. And essentially what you see is that Hansen took, these were untrained people, and she and her colleagues did a one-legged kicking model. So one of the legs essentially would train essentially 6 days a week, 75 minutes a session, while the other leg would do session 1. They would not eat any carbohydrates for 2 hours and then do session 2 right after. Both groups did 6 sessions, but one group was in a low endogenous carbohydrate situation every second session. So if you look here at the total work pre-training and post-training, you can see that the total work actually went up more in the low carbohydrate group than the high. Okay, so there was, when they did a time to exhaustion trial, they were able to do more total work. So this actually improved performance. Also, if you look, citrate synthase, which is rate limiting enzyme in the Krebs cycle, very important for performance. You notice that it was higher in the low endogenous carbohydrate condition than the high. Okay, as well as HAD, which is 3-hydroxyacyl-CoA dehydrogenase. This essentially is important for fat oxidation, and of course, citrate synthase, as I've already discussed. So, how does this work? What are the mechanisms of action? One of the first things to realize is that low glycogen increases the activity of adipose triglyceride lipase and hormone-sensitive lipase. If you have an increased circulating free fatty acids, that's important for at least 2 reasons. 1, it provides substrate for oxidation in the mitochondria, and 2, it acts as signaling intermediates for transcription factors and nuclear factors that regulate the proteins involved in transport and breakdown of lipids. So if we look here at plasma-free fatty acids, actually we look at glucose, this is the low glucose condition. Okay, so they're not consuming carbohydrates during the session. Then you see up here, this is fatty acids. Notice that the low glucose condition has the highest fatty acids, while the high glucose condition has the lowest fatty acids. So again, if you look here, one of the things, if you look at this figure, is that liberated fatty acids can activate a complex known as the perioxyme proliferator activated receptor, or PPAR. So we have PPAR alpha/gamma, and when PPAR alpha/gamma is activated, it controls the transcription of fatty acid oxidation enzymes such as carnitine palmitoyltransferase 1 and 2, fatty acid translocase, hormone-sensitive lipase, and it also associates with PGC1 alpha to regulate mitochondrial biogenesis. Catecholamines appear to play a very large role in this mitochondrial biogenesis activity. So, and that's very, very important. In fact, if you have beta-adrenergic receptors blocked, 70% of the exercise-induced increase in PGC1 alpha activation is decreased. Now, PGC1 alpha, remember, is one of the master regulators of mitochondrial biogenesis. So, clearly, an increase in epinephrine is important for this. Now, if you look at plasma adrenaline levels at the top, which is A, you see the low glycogen state. It's actually reversed. So the low glycogen state's the upper one, and the high glycogen state's the lower one. So you can see that adrenaline is higher. So the point is that that's going to activate and phosphorylate the cyclic AMP response element, and that's again one of the targets of PPAR gamma coactivator 1 alpha, or PGC1 alpha. So here's sort of the model that we have. We have cycling bout 1, no carbohydrate. cycling bout 2 were in a low endogenous state. That's going to increase AMP. That's going to activate AMPK. That's going to switch on transcription factors, which increase fatty acid oxidation, mitochondrial biogenesis, and finally endurance performance. So let's talk about AMPK. The thing about AMPK is that it has 2 glycogen binding domains. That includes the glycogen binding domain and the carbohydrate binding domain. So this basically, the point of this is it allows AMPK to sense when glycogen is low in the cell. Okay? But when glycogen is high, it blunts AMPK's ability to work because you have high availability of energy. So again here, we see that AMPK is bound to glycogen in a high glycogen state. However, here, we see AMPK is liberated to upregulate various genes involved in endurance performance. So Yale actually looked at trained people. Remember Hansen looked at untrained people? What we had them do is train 3 100-minute workouts at 70% VO2 max and 3 workouts at 5-minute intervals at 100% VO2 max. Each of these is known to drain glycogen by about 50%. So we had the high endogenous situation in which they were divided the daily training sessions over 6 days. And then we had the low CHO condition, and they completed the training sessions on the same day. So they do the low intensity, 2 hours later they'd follow up with the high intensity. Okay, so what I want you to really look at here is figure 5. Okay, you see what happened is what they did before the study started, they did a 60-minute steady state run. Okay, now what I just pointed to right here, that this is the high carbohydrate group. This is how much fat they oxidized from 10 minutes to 15 minutes before and after training. Now if we come over here, this is the low carbohydrate condition. So basically they're looking at how much fat they're oxidizing during a 60-minute steady state run at 70% VO2 max. That's their oxidation before and that's after. Now this may have important implications for body composition because it indicates that you make these adaptations which allow you to metabolize fat at a higher rate. We also see greater molecular adaptations in the low group and enzyme activity and content. So you can see citrate synthase activity in the low group is higher than the high group, as well as BHAD. Also, you see cytochrome C oxidase subunit in the D figure is higher in the low than the high. And this is pointing those things out. Citrate synthase, BHAD, as well as cytochrome C oxidase. Now, what I want you to notice, this is very interesting. What we're looking at is the percentage of peak power individuals were able to maintain when they did the high-intensity training. Remember, the low carbohydrate group, which is the open squares, completed their high-intensity training 2 hours after the long, low-intensity bout. Notice that their work output is much less than the high carbohydrate group. Remember, the theory is that if that happens because of high carbohydrate availability, adaptation and performance will be better. We already saw molecular adaptation was not better. And if you look at power output here in the high group, you see from pre to post it went up. It went up from pre to post in the low group as well. Basically, they went up 10 and 12% respectively. No difference in performance despite the higher intensities maintained in the high group. So one of the things that we think is that a lack of performance benefits ultimately suggests that the observed carbohydrate sparing is more likely to be an impairment in carbohydrate oxidation due to a downregulation of the multi-enzyme complex pyruvate dehydrogenase. We're going to discuss this later, okay? What you're seeing here in this graph, however, is one of the things that's regulating this increased fat oxidation in the low group. So basically, after training in either the low endogenous or high endogenous, you see CD36 increases more in the low than the high. So CD36 basically plays an important role in fat oxidation transport across both the plasma membrane as well as mitochondrial membranes. And it also contributes to the regulation of fatty acid oxidation. Also, what I just highlighted here, right here, is muscle triglyceride levels. Notice that intramuscular triglyceride levels increase from pre-training low to post-training low. Now, the next question is, what about exogenous availability? You know, how does that impact adaptation? Well, we have a study here where they had 6 weeks, 3 days per week, 1 to 2 hours at 75% of peak VO2. These were moderately active males with or without carbohydrates. Now, here's the thing that I want to point out. There were no differences in fatty acid oxidation after training or VO2 max. However, it appeared that the onset of molecular adaptations for fat metabolism were beginning to take place. As you can see here in graph A, the fasted condition, essentially and they were training basically, again, they had with carbohydrates during or not carbohydrates during exercise. And you see CD36, fatty acid binding protein, are elevated to a greater extent in the fasting condition than the carbohydrate condition. We also see hexokinase is higher and GLUT4 translocation is higher. So this does seem to be triggering a lot of these molecular adaptations despite no difference in performance. Now, one of the questions is, what about what happens when you have low endogenous but high exogenous? Okay, can you blunt the adaptation then? So basically this study by Morton had 4 high-intensity intervals per week, and they had 3 groups. First group was twice a day. Right here, this is the first group. So basically it's a low endogenous plus placebo. So they trained twice a day, 2 times a week with no carbs during session 1 or session 2. So that's called a low exogenous, low endogenous, meaning in the blood and in the muscle, respectively. Secondly, twice a day, in the second group, which is here, they also trained twice a day, and they depleted in the first session. They didn't have any carbs in the interim. However, during the session, or right before the session and during, they did have carbohydrate. So that's low endogenous and high exogenous carbohydrate availability. And then the final group did 4 sessions per week, spread out throughout the week, and they had adequate carbohydrates, so they had high endogenous, high exogenous each session, and that's right here. Here's what I want you to notice. So this right here is the low carbohydrate, or the low endogenous plus carbohydrates during. This group is the low carbohydrate plus placebo, so low endogenous, exogenous. Here we have the normal group, and that again, they're training with high carbohydrate availability every session. What I want you to notice is that the succinate dehydrogenase activity, which is a critical enzyme in aerobic metabolism, increased to a greater extent in the low plus placebo condition than all other conditions. We also see something similar here in the vastus lateralis, right here. Okay. So this is a sort of a real important study, and basically the next question is, what if you had super high carbohydrate availability versus moderate? We've talked about low versus high. What about moderate versus high? Does the high enhance adaptation? Because that's always what people say. Well, basically you have the moderate carb group, and they had 5.3 grams of carbs per kilogram per day. Then you have the high carbohydrate group, and they essentially had 8 grams per kilogram per day. So basically they had their normal carbs plus carbs during training. Now one thing I want you to notice is that if you go over, a real interesting finding is that citrate synthase activity appeared to be greater in the high, or increase more in the high than the low. Although it's difficult to see that that increase is that much different. But it is a surprising finding based on the past literature. Now, what I want you to see here is time, essentially time to exhaustion, and, time trial performance. If you look at the water condition, this is the low carbohydrate availability condition, so or moderate carbohydrate availability, excuse me. What you notice here is that in the water, before and after their performance is not different, and in the glucose, before and after their performance is not different. But the same thing happens with the high carbohydrate group. Okay. In addition, if you go over the fat oxidation graph, fat oxidation seems to be similar between groups. So what this indicates is that going above 5 grams of carbohydrate per kilogram, while it may augment performance during overreaching situations, may not lead to better adaptations. But one thing that should concern you is that if you go very low carbohydrate, like 2.5 grams per kilogram versus 10, essentially the lower carbohydrate will blunt pyruvate dehydrogenase activity, and thus the ability to use CHO. But CHO, or carbs, are very important for high-intensity exercise. So if you look here, the fat-adapted group, basically after 5 days of becoming fat-adapted, their pyruvate dehydrogenase activity had decreased compared to the high-carbohydrate group. If you look at sprinting in the gray group versus the fat group, the actual sprinting performance was greater. So let's summarize this lecture up. Chronically low carbohydrate, less than 2.5 grams per kilogram, may impair carbohydrate oxidation. Right, so you might not want to necessarily do that. There is an alternative, and that's to train adequate half the time and depleted half the time by training twice daily. This appears to increase metabolic adaptations, but not improve performance when work is not matched in training. Also may improve body composition based on the fat metabolism data, but that needs further exploration. Carbohydrate availability may modulate adaptations, and there's conflicting evidence, though, that suggests that not having carbs during training could cause favorable adaptations, but only performance increases in untrained individuals. The combination of low carbohydrate in the second training session with low exogenous carbohydrate may be ideal for adaptations as compared to high exogenous during the second session. A high carbohydrate doesn't appear to improve performance over moderate carbohydrate, even when extra is given during training. However, moderate and high carbohydrates might be ideal for high-intensity bouts as compared to very low. It's likely that some sort of nutrient periodization is necessary to optimize the effects of low and high carbohydrate availability. As far as body composition, again, this has not been investigated, but implications are we do know the ability to utilize fat is enhanced, and theoretically training in a depleted state every other session could lead to positive body composition changes, but this will need to be investigated further. Thank you very much for your time. That concludes the carbohydrate section of our course.